In the previous presentation, we had discussion on the concept of short circuit and an open circuit. Now in this presentation, we will be talking about the basic circuit element capacitor. Like a resistor, it is also a two-terminal device, but the characteristics of a capacitor is totally different from that of a resistor, because resistor is used to consume energy or to absorb energy, and the capacitor is used to deliver the same amount of energy as absorbed by this device. So capacitor is basically defined as capacitor is a two-terminal device used to store energy in its electrical field. The symbol for the representation of a capacitor is like this. The straight bar will represent the positive side and the curved bar represent the negative side of this capacitor, and C is the capacitance of a capacitor, and Vc is the voltage across the two parallel plates of this capacitor. The basic construction of a capacitor is to separate two parallel metallic plates with a specific distance, let's say d, and these two metallic plates are having the same area, and the medium used between these two metallic plates is air or any other dielectrics. Now, to understand the capacitor in a more brief way, let's take an example in which we have a capacitor which is connected in series with a resistor and a switch and a DC voltage source. Now, when this switch is open, so there is no current in this circuit, so as a result there is no net positive and negative charges on this capacitor on these two parallel plates. Now, at the instant when this switch is closed, so the positive terminal of this battery will attract electron from this metallic surface, and this negative terminal of the battery will repel electron towards this bottom plate. So as a result, the positive charges will be established on the upper plate of this capacitor, and the negative charges will be established on the bottom plate of this capacitor. So the number of electron attracted by this positive terminal will be equals to the number of electron repelled by this negative terminals towards this bottom plate. So as a result of this, the current will be established from the positive terminal of this capacitor towards the negative terminal of the capacitor, and this flow of charges will be continued until the potential difference across this capacitor is equals to the potential difference across this source voltage or this source. Now, at the instant when the voltage across the capacitor is equals to the voltage across this source, so the flow of charges will be stopped, and a net positive and negative charges will be established on these two plates. As we discussed in the video of a DC voltage source, is that if there is a region of positive and negative charges in a device or a component, then that component is used as a source to deliver the power. So in that case, if we separate this capacitor from this circuit and connect it across a resistor, then the capacitor will be deliver the same amount of energy as absorbed by this capacitor. The capacitor shows its true characteristics only when the changes in current or voltage is made. So initially, when the switch is open, there is no current and there is no charges on these parallel plates, so there is no potential across this capacitor. So as we connect this switch, the flow of charges will establish from the positive terminal towards the negative terminal, and the charges will getting stored on the plates of this capacitor, and the potential difference will establish on the plates. So initially there is no potential difference across these plates, so there is no current in the circuit. So as the rate of potential difference increases across this capacitor, the current through the capacitor increases. So the current through this capacitor is directly proportional to the rate of voltage across this capacitor. Now, at the instant when the voltage across this parallel plate capacitor is equals to the voltage across or the potential difference across this source, so the voltage become constant and the rate of voltage is equals to 0 at that instance, because when V is constant, when the voltage across this component is constant, then the rate of voltage is constant and the current in that case is equals to 0, because when the potential difference across this capacitor is equals to the potential difference across this battery, so the current flow at that instant would stop, and a net positive and negative charges will be established on the plates of the capacitor. So to remove this sign of proportionality, I is equals to C. C is the constant of proportionality, and this C is called basically the capacitance of a capacitor, dV by dt. Now to find out V from this equation, I divided by C divided C on both sides is equals to dV divided by dt. Now multiplies dt on both the sides, so we get IC dt divided by C is equals to dV. Now to remove this derivative, we can take integration on both sides. So by taking integration on both sides, the derivative will cancel integration, so V in this case is equals to current and capacitance in this case is constant, so 1 over C into I, and the limits of this integration is from 0 to some time t, because at time t is equals to 0, at the instant when this switch is closed, there is no charge on the capacitor. After some time t, the potential across this parallel plate capacitor is equals to the potential across this battery source or this voltage source. Now from 0 to t dt, so potential is equals to, in this case, 1 over C into I. Now the integration of dt is t, and the limits is from 0 to t, so we get V is equals to 1 over C I t. Now as we know that the current is equals to the rate of charges, now charge is equals to IT. So putting Q instead of IT, we get V is equals to 1 over C into Q. Now we can rearrange this equation in the form Q is equals to CV, where Q is the charge on the capacitor charge and measured in coulomb, and C is the capacitance of a capacitor, and V represent the potential difference across the capacitor, potential across the capacitor. Now what is capacitance? Capacitance is basically the measure of capacitor ability to store charge, or simply we can say that the storage capacity of capacitor is known as capacitance. And from the above equation we get C is equals to Q divided by V. So the unit for capacitance to calculate the capacitance of any capacitor is a farad, which is represented by F. Generally farad is a larger unit, so microfarad, nanofarad and picofarad is also used to calculate the capacitance of any capacitor. So it's all for today's presentation. If you have any doubt, ask in the comment section. In the next presentation we will be discussing some important points about the capacitor. See you in the next one.